Our purpose in studying coordinate transformations is to try to apply them toward evaluating integrals in a more straightforward way. When we have an integral like this, we are taught to make a substitution. X is 2u, dx is 2du. The limits of integration change. When x is 0, that tells us that u is 0, and when x is 1, that tells us that u is 2. This 2 is really x prime with respect to u. Applying this transformation tells us that the integral can now be rewritten in this alternate form, and this factor helps us understand this distortion idea. Now, we've also seen this in the context of double integrals. So, for example, we've taken double integrals that were complicated in one coordinate system, and we've changed them into some other coordinate system. Doing that allowed us to simplify integrals because the area distortion factor allowed us to find antiderivative formulas. Now, what we would like to do is find this area distortion factor for a general coordinate transformation. So to that end, we're going to consider the following. We want to take some elementary region D star, and we want to apply a coordinate transformation to turn this into some other elementary region. Under this coordinate transformation, which we'll call x of u and v and y of u and v, we want to know this area distortion factor. So we're going to go through an analysis here to determine what that area distortion factor is. Now we're going to let t be a C1 transformation. And what that means is that both of these functions x and y are C1. That means they have continuous first partial derivatives. So x can be differentiated with respect to both u and v, and those functions will exist and be continuous functions. We're going to talk about an integral that's given as such in the xy coordinates, and we'll say that f is continuous, which means that the function will be integrable. As always, we're going to try to come up with our results by using a subdivision idea. So if we take our elementary region here, we would normally start by using a basic rectangular region, coming up with our results for that rectangular region, and then defining an extension function. But we already know the results that are going to happen here. So let's jump straight to this concept here of subdivisions. So we're going to have a regular partition for both of our u and our v values. U will be partitioned u0, u1, all the way up to un. Some general point will be defined as follows, where delta u is equally spaced into n subdivisions. And at the same time, we'll have v0, v1, all the way to vn. V will be indexed on j, and delta v will also be defined with n subdivisions. So effectively what's happening is we are taking this box that's bounding our elementary region, we're cutting it up into lots of little rectangles. We'll only consider what happens to rectangles that fall in our elementary region because we're essentially skipping the function extension step. Now, according to our transformation, this is going to get changed into some other region in the xy plane. Now, the big difference here is that we have no idea what the resulting regions are going to look like. And in fact, there's no reason that we should expect them to turn into rectangles anymore. So some rectangle here will just turn into some general patch over there. Now, we're going to consider this general box Bij star. And this box will have one of its corners being at ui vj. This corner will be at ui plus delta u vj. This corner up here will be at ui vj plus delta v. Now the image will generally be some sort of patch. And the question that we want to know is, how does Bij star get mapped to this patch? This seems like a very challenging problem, but there's one key idea that saves us here. This transformation is a C1 transformation. That means that both of these functions are C1 functions. The derivative of x with respect to u, the derivative of x with respect to v, the derivative of y with respect to u, the derivative of y with respect to v exist and are continuous. If they are C1, that implies that both of these functions are differentiable. They are locally linear. Both of these functions, x and y, are well approximated by a linear approximation. So if we go back and we consider a linear approximation for this function of two variables, we are going to base it near one of the corners of our box. So let's say ui and vj. That means that this function is approximately equal to this expression evaluated at all of these points. And similarly, that the function y is also well approximated by this linear approximation. And again, all of these functions and all of these derivatives are evaluated at some point that we'll just call ui and vj. We could rewrite it as column vectors. We'll group together these terms. And I'll just use some shorthand notation for these partial derivatives. And remember that each of these partial derivatives is evaluated at the same point ui and vj. If we were to call this our vector x, this will be some vector b. Here's a matrix A. We'll call this u. We have an affine transformation. T is well approximated by this affine transformation. That means that the image of this box Bij star, which is a parallelogram, will then be approximated by another parallelogram in this xy plane. And if we want to try to visualize this, this is saying that if we were to take this box Bij star and apply the transformation to it, yes, we might get some strange patch like this. We could replace it with a parallelogram. The error in using the parallelogram wouldn't be that bad. They'd be a good approximation to the box. If we've got a parallelogram and we know a vector on this side and we know a vector on this side, the area of this parallelogram will simply be A cross B. We need to know what these A and B vectors are going to be. Take this point here in the corner to be ui and vj, and we'll say that it maps to this point, T of ui and vj. Now, the other points we're going to be interested in here are ui plus delta u and vj, and this point up here, ui and vj plus delta v. Now, to try to help us visualize this, what we'll do is say that this is the image of our parallelogram here. This first vector there will correspond to tui vj. We'll say that this second vector here corresponds to tui plus delta u and vj. We'll take our vector that goes between them to be A. It's a bit of an abuse of notation, but we'll say that A is going to be the difference in these two expressions. And if we were to use what we have from above, tui plus delta u and vj, remember that this was the same as finding the linear approximation near that point and then applying this affine transformation to it. Over here on the side, we would plug in our two values, and what would end up happening is that we would get T of ui vj plus this xu, xv, yu, yv times delta u and 0. And if we were to just expand that out using the definition of this matrix times a vector, what we would find would be another vector, xu delta u, yu delta u. Now that means that the vector A will then just be T of ui vj plus column vector here, subtract a T ui vj. Clearly those go away, so the vector A is simply this vector with a partial derivative u in that case. We can do the same thing to define what the vector B is going to be. So if we were to take our parallelogram again, just like so, as before, this bottom corner, tui vj, this top corner up here will be tui vj plus delta v, and the vector that we are interested in is this one b. b will simply be the difference in those two. And if we repeat the same process that we did from above, what we would find was that b would be the x partial derivative with respect to v, delta v, and the y partial derivative of v with respect to v. So the area of this parallelogram image is just going to be the cross product of those two. We'll get an I, a j, and a k. A was xu delta u, yu delta u, 0, xv delta v, yv delta v, and 0. Computing the cross product is going to give us a 0 component there in the I, a 0 component in the j, and in the k component, we'll have an xu yv minus an xv yu, both of them multiplied by this term. So then the magnitude of this expression is simply going to be the square root of this quantity squared. And because delta u and v are always positive, they can get removed. This is an absolute value of this product of partial derivatives with this delta u, delta v. Another way to write this is in matrix form, xu, xv, yu, yv, and you can see that it's a determinant of this matrix. But because we have an absolute value, we have to put this double bar. So another way to think of it would be the absolute value of the determinant of this matrix like so, times a delta u and a delta v. Now for shorthand notation, this is sometimes given the letter J, or we like to write this strange notation. This is what we are going to call the Jacobian. Sometimes it's called the Jacobian determinant, and we usually put that it's a function of u and v, kind of like this. So that means that the area of the image of this box Bij is then the absolute value of this Jacobian, delta u, delta v. Remember that we are trying to find the volume under a function and above one of these patches. So the volume under the function f and above the image of this Bij star is then approximately f of x at ui vj, y at ui vj, times this Jacobian, delta u, delta v. The total volume is then approximated by a double sum, I equals 1 to n, j equals 1 to n, f evaluated at xui vj, yui vj. This Jacobian, each one of these Jacobian terms is evaluated at the ui vj, delta u, delta v, and then the actual volume is a limit as n goes to infinity of this double sum, I equals 1 to n, j equals 1 to n. All of this stuff right here, remember that this is a Riemann sum, and so all of this stuff in the blue box gets to go there, delta u, delta v. And because f is continuous, and because these x and y are C1, each one of these partial derivatives that we'll find in the Jacobian times our function f is also continuous. And that means the integral exists. And finally, we've come to the conclusion that we're looking for. If we have an integral and we know a transformation, we've now come up with a general formula for this area distortion factor. It's the absolute value of this Jacobian. We sometimes write these notations. The x and y go up top because they are the functions. The u and the v go on the bottom. And it's the determinant of this matrix of partial derivatives. In the next video, I'll show you examples of how to transform and how to evaluate this Jacobian.